good
It has
thing.
to, it has to call me.
Except
Like,
for-
everyone-
except for when
everyone's
they
like,
were
you
doing
do a
the,
push, and I'm like, 99% of the time,
flux,
it won't even
They
give
want,
me
they
the option of.
put in the form of
Or it takes so
a
long.
I said, that's enough for you to do that.
All right,
Right here.
let's get started. Couple things.
Who was that?
First, yes, thank you. Homework. Please turn in your homework. Secondly, it's almost time for our midterm. So the midterm, I think it's scheduled for 2 weeks from today. If you look at the syllabus, but that's, I'm thinking that's still gonna be the plan. So we only have 2 tests. We have midterm, we have finals. So the midterm is 2 weeks from today. Is that what it says?
18th of October.
18th? Yeah, that would be 2 weeks from today, right? Today's the 4th. So next week, we're actually going to just review for the midterm. So I'm not gonna give you any new stuff next week. But if it's clear, we're still gonna go out to the observatory next week. And right now, you can believe 7-day forecast. It looks like it'll be good next week too. And then we'll see how it goes the week after that, because I think the week that we're doing the test, the moon's starting to come around again and get bright again. So right now, we're in a perfect thing. No moon, nice dark sky, so it should be good. So that's the plan. And then after midterm, then we'll start doing more stuff and all the way into the final. The final is the last day of class. It's not during finals week because we're a non-standard class. You do it on the last day of class. So, all right. Today, by the way, any questions about the homework you just got back? Couple things. I want to mention one couple things. Most of the problems, most of the things that people got wrong was drawing the pictures, which is not a surprise. But we always draw with north here and south here, right? And then when you draw this, that puts east back here, west back here. But some of you, when it went to the one from the southern hemisphere, flip the north and south. But if you flip north and south, it also flips east and west, right? It rotated the whole thing. It's easier to do it the same exact way. Don't change this. You still then have east and west here, but then your south celestial pole is here. I think it was what, 41 degrees or something, is on this side. Or if you flipped it around, most people forgot to put east and west, and so then they actually had the hour angle on the wrong side, because the positive and negative would switch sides, right? Because negative is always on the eastern side, positive is on the western side. Whether you're in the southern hemisphere or northern hemisphere, that doesn't change. Does that make sense? Some of you did it right and some of you did it really well, but that was the biggest thing I saw with people that flip this around, because if you flip this around and put south over here, north over here, you can do that, but then this becomes the east, that becomes west. And you've changed which side, the front and the back is east or west.
If we did it south, it would be in the back.
If you did it this way, that would be all right. Then your south celestial pole is going to be over here, 41 degrees, your south celestial pole is here. It's just the ones on this side towards us over here, towards the east, this is now the negative side. The positive would push it back there.
So our angle would be on the opposite.
Yeah, so the +2, I think it would have been way back there, not on the front side. Okay. I know it's tricky. It is tricky. All right. Today, I want to talk about telescopes. Hopefully, most of you got a little bit of telescopes from one of your astronomy classes, right? Talk about how telescopes work. Fairly simple objects. One of the questions is why telescopes weren't invented hundreds of years earlier. Because they had lenses from about the 1400s. But the telescope wasn't invented until about 1609. So why didn't it take, all you have to do is put two lenses in the right combination, you get a telescope. Why did it take 200 years to figure that out? Usually, if you're just messing around with lenses, you think you'd get lucky and just figure it out, right? I don't know, but that's the way it ended up working out. All right, and it is possible that somebody else invented it before Hans Lippershey, that we get credit for, but it is never recorded or got lost to history, and we just don't know, right? It could have been invented, China or somewhere else too, and we never knew. That's the way a lot of things are. All right, so first of all, why do astronomers want big telescopes? You can ask an astronomer, no matter how big the telescope they have, they want a bigger one.
More light.
Why? Why is more light good?
Higher resolution or resolving power.
That is true, but that's actually not the limit. We're going to talk about that today.
You get to see more stars.
Because you see what?
More, you can capture more light.
Right, so you can see,
More stars.
yeah, fainter objects, right, which gives you more stars, right? So what you can see is fainter. I always like to tell people, especially when I'm talking to the public and they don't really understand this, like, why do you want a big telescope? It's like, what if you were catching rain in a bucket? So it's raining and you have a bucket, you're trying to run around and catch rain. If you want to catch more rain, what do?
Get a bigger bucket.
Get a bigger bucket. Okay, so when we have telescopes, and we have, this is an 8-inch telescope over here. The ones that you guys are using are 10-inch telescopes. So is the 10-inch telescope 25% more light gathering than the 8-inch?
No,
How much more?
not to wait. 8 times?
What? How much more light does a bigger telescope get than a smaller one? If I had a telescope that was twice as big, let's do an easier example. If I have a 5-inch telescope and a 10-inch telescope, do I gain twice as much more light?
No,
How much more do you get?
8 times. Isn't it?
No,
It's something.
it has to do with the
Radius of the.
area, right? Because it's the area that's collecting the water, right? So this, we're catching light instead of water, but the idea is the bucket, right? So it's the area. What's the formula for the area of a circle? Pi r squared, right? So if I want the ratio of two different areas, area 1 and area 2, essentially I'm comparing two telescopes. I'm comparing the area that they have. This is just pi r1 squared over pi r2 squared. What happens to the pi's? They cancel. So the ratio of area 1 to area 2 is really just equal to r1 over r2 squared. So my example, we're at a 10-inch and a 5-inch. 2 squared is 4. You get 4 times as much light. Okay. Let's compare this. Telescopes you're going to use tonight are a 10-inch telescope, right? How many millimeters is that? I think there's 24 or the 26 millimeters per inch. Something like that, 24 millimeters per inch. Right, and you have a 10-inch telescope, right? So the inches cancel, you have 241 millimeters. That's probably about right. Yeah. That's the diameter, right? I don't know. The convergence rate, I'm trying to do it from memory. Okay, but how big's your eye? At maximum dilation, meaning the pupil's as big as it gets.
About 7.
About 7. Now it does vary by person. If you can get bigger, you've got better night vision. That's why cats, you ever seen a cat in the dark? Their pupils actually get up to 9 millimeters. They get bigger than the human eye. So they have really big pupils. That's because they're really good at seeing in the dark. So when you're running into furniture, the cat's just walking around like, eh, they're stupid. Cats usually do that anyway, right? How much more light does your 10-inch telescope get than your eye? We would have to put 241 over 7
Wait, wouldn't you have to
squared.
divide it by 2? Because that's a diameter. not-
Doesn't matter. Yeah, this is a radius, right? She's like, oh, it's a diameter, you have to divide it by 2. But if I divide this by 2 and I divide this by 2, what happens to those 2's? Right? What do I do when I have a
Well,
fraction in the
I-
bottom?
I know that they cancel out, but I mean, shouldn't you do the radius rather than the diameter?
What I'm saying is it doesn't matter because the 2's cancel. So you can do either the radius or the diameter. It's going to give you the same exact value. Okay. As long as you're doing the same in both of them. Let's see how much more light our telescope gets. So 241 divided by 7. Now we got to square it. I get 1,185. And there's no units, it's just 1,185 times more light is gathered by the telescope in your eye. That's why it's a big advantage. What's the biggest telescope in the world? The what?
Okay.
Keck telescope currently. Now there's other ones being built,
It's like almost.
but none of them are working yet. The Keck is. How big is the Keck? Anybody know?
30 meters?
10 meters. 10 meters in diameter. So if I put that into millimeters, that's 10,000, right? Divided by 7, we're going to compare it to how much more it is in our eye. You get a big number. Yeah, you square that. Yeah, I got 2,040,000. 2 million, it's close enough. So the Keck telescope can record light 2 million times fainter than our eye can. Okay, so if I'm asking you a question like this on a test, simple, just take the diameters, divide them, and then you square that, right? It's the ratio of the two. Okay. What about our 10-inch to an 8-inch? Does it matter that they're not in millimeters?
No.
No, as long as these guys are in the same units, that's all that matters. So 10 over 8 is 12825 squared, which is. Did I do that right? Yeah. Yeah, so about 1.5 times, or about 50% more light. 2 inches bigger, 50% more light. So, what's the biggest telescope we have at the observatory? 1 meter. And we have a 27-inch.
Oh. 16 is the tiny ones, right?
16 is the one in the other dome.
Okay.
So we got 27, 16, 10s, 8s, 5s,
Good, I was
4s.
right that we didn't.
So the 27-inch compared to the 10-inch is what? 2.7 squared. I can't do squares in my head. About 7 times more light. All right. Make sense? Yeah, you gotta go by the area. By the area. All right. Now, let's talk about angular resolution. What is angular resolution? What's angle? Yeah, how tiny you can see separation, right? And with your naked eye, what can you see? What level can you see to?
About 60 arc seconds, is it? One arc minute.
Actually, several arc minutes, yeah. It depends. Some people's vision is better than others, but usually on the order of 4 or 5 arc minutes typically. Now, there are people with better, and there are animals. They've tested things like eagles, and they can see down to sub arc minute resolution. What they do is in the back of their eye, their sensors are just actually more packed than ours. They're tighter together, so you get slightly higher resolution. That's why they can be up there at 500 feet, pick out a mouse from below it, right? Catch the movement. All right, angular resolution then is how small or how much separation you can see. So if we had 2 stars that are fairly close together, like 5 arc seconds apart, the question is, how big a telescope do you need so you can see this 2 stars? Or does it just blur into one big star? Now, what limits you and your ability to see that is the nature of light itself. Light is a wave, right? And when the wave comes through, you don't actually get a nice precise point from a star. You get a what they call an airy disk pattern, where most of the light comes through in the center, but then you actually have these rings of light. They're called diffraction rings. It's because light is a wave. Whenever it hits an object like a lens or anything like that, the wave doesn't hit it cleanly. It's not like a ball bouncing off something. It's the wave front hitting it. And every time it does that, it separates the wave out, makes it a little bit bigger. So the problem is when you have multiple waves, these waves start to overlap. And if you get them too close together, it just appears as one big wave. That's the limit. Now, the bigger the telescope, the more you can separate those apart, which is the angular resolution. And there is an equation for this. The sine of theta is equal to 1.22 lambda over d. Now this is a little tricky because those have to be in the same units. So this becomes a ratio. Usually lambda is the wavelength you're looking at. So it depends on what wavelength you're actually looking at. We're humans, we like visible light because that's what our eyes detect. And so we usually use a wavelength of about 5,000 angstroms. Have you heard about an angstrom? Yep. Some people have. It's kind of become an old unit, meaning I grew up with it, but now most astronomers don't use it anymore. But it's hard for me to change after teaching for 30 years. This angstrom is actually comes from Norwegian or something like that. Not sure exactly, but it's not normal. But that's equal to 5,000 times 10 to the minus 10th. That's what an angstrom means, meters. Well, that's a non-standard metric unit. What most people have gone to is nanometers. What's a nanometer? 10 to the negative 9. So how many nanometers would 5,000 angstroms be? Yeah, this is 10 to the 9th, but this is 10 to the 10th. This would be
No, 5,000.
500.
500. You got to go the right way. So this is equal to 500 nanometers. Yeah. Which is equal to 500 times 10 to the minus 9th, right? Or 5 times 10 to the minus 7th if you do it in standard scientific notation, which means the first number shouldn't be bigger than 10. It has to be single digit, essentially. Am I confusing you totally? All I do is converting units. All right, so let's put in our 10-inch telescope. for the diameter here.
You can have like standard wavelength for any.
Yeah, so the standard wavelength we usually use is this. That's the wavelength of green light. And green light is right in the center of our spectrum. We talked about this the other day. So that's the center of the visible spectrum. Remember red, orange, yellow, green, blue, violet, Roy G, Bilby, whatever they want to call it. So that's what we usually use. But if you were going to calculate for infrared, like the James Webb Space Telescope they're putting up is actually an infrared, you would shift this. It wouldn't be 500 nanometers. It gets longer. It would be a couple thousand, probably 3,000 or 4,000 nanometers. I'm sorry. Yeah, 3,000 or 4,000 nanometers. Gets longer into the red, right? All right, so let's just plug this in. This is going to be 1.22 lambda 5 times 10 to the minus 7th over our diameter. Remember our 10-inch times. I can't remember what the conversion is, but it's,
2.5
what is it? 25?
in a millimeter, yeah,
25.4? I can't remember. It's something like that. So 254
yeah, it's not bad.
millimeters, right? I know it's 24 or 25, somewhere in that range. So, but we want this in meters. So what are we putting down here? Because this is in meters, right? So this has to be in meters too. So this is 0.254 meters. All right. Notice when you do this, this is a little tricky if you haven't done this before. So you got 5 to the negative 7 divided by 0.254 times 1.22. You get a really tiny number. In fact, on your calculator, mine goes scientific because it's times 10 to the minus 6. Scientific notation. But I want to know what theta is. So if I have sine of theta equals that, how do I get theta?
Inverse.
Yeah, you have to take the inverse sine of that. So this is sine of theta. But theta is going to be the inverse or the arc sine of this value, which is 2.4015 times 10 to the minus 6. I did it right. Now, what we want to do is we want this angle to be in degrees. So make sure your calculator is set to degrees. If it's set to radians, you'll get the wrong answer, or you'll have to convert. So the inverse sine of that value. I get this. I get that theta is equal to 1.376 times 10 to the minus 4th degrees. But I don't want that as degrees. I want it in arc seconds. So what do we have to do? Convert, right? So we have to say, oh, 1 degree is equal to 60 arc minutes. Remember, a single slash is arc minutes.
Mhm.
And then 1 arc minute is equal to 60 arc seconds. So we're really just going to take this times 3,600. That's what 60 times 60 is, right? To get the value, because we always want it in arc seconds. And you get 0.5 or 0.495. Arc seconds. What if I had a bigger telescope? If I have a bigger telescope, this number gets smaller. Right? But will I see any better?
No.
Why?
Because you were diameter. The amount of light coming into the telescope.
No, the bigger is the more light, right?
Oh,
If I get bigger, not only do I get more light, but I should be able to see the finer and finer detail. Not really. That'd be nice in reality, but it's not. The problem is we live in an atmosphere. And our atmosphere limits our viewing to about 1 arc second if we're lucky. The reality is it's closer to 2 arc seconds in Texas. Meaning, because the starlight has to pass through our atmosphere all the way to us, we'll talk about this in a few weeks when we talk about atmospheric change. It spreads out the star, and it doesn't matter how good your telescope is, you can't make it appear any smaller than the atmosphere lets you. Now you get around that by not putting your telescope on Earth. So where do you put your telescope? In space, and if you put it in space, then you're actually only limited by this, and the bigger the telescope, the better it gets. That's why the Hubble Space Telescope is about 2 meters across. That's as far as I can reach. Okay. There's way bigger telescopes on the Earth, but the Hubble Space Telescope is in the ideal location. It's in space, so it doesn't have to deal with the atmosphere, and so it gets superb resolution. Instead of seeing down to about 1 or 2 arc seconds, it can see details down to about 1/100th of an arc second, just because it's in space. You know what's really cool? Is the James Webb Telescope is about 5 times the size of the Hubble Space Telescope. When they launch that, hopefully it works. Yes, keep your fingers crossed. The resolution will go up even more. It's going to be amazing, right? They've been trying to launch it for more than 10 years. So, but it's supposed to launch in like 2 months, December. Finally.
What was the issue for why it wasn't launching?
Well, it's been a series of things. First, it's like 3 times over budget, typical. They had some problems with design and all that, and then there was problems with changing administration, not wanting to pay for it. You know, that's the problem when you live in a country where every 4 years you shuffle everything. Then they change their attitude and they say, oh, we don't want to spend money on this. And then the next one says, oh, we do, and it kind of goes. And it's just been a series of things. But it's supposedly, it's all working. It did all the final tests and it's all ready to go. And so, yeah, it was supposed to be launched years ago, like 3 or 4 at least. Back when they planned for it, it was supposed to launch by about 2010 because it was supposed to replace the Hubble Space Telescope. Here we are 11 years later. Well, the Hubble's actually still working, which nobody believed it would. But the Webb hasn't launched yet, so that's the way it goes. All right. Questions about this? The key to using this equation is making sure those are in the same units. Okay, and then when you get your angle in degrees, convert it to arc seconds. Yeah.
It's kind of off, it's not necessarily off topic, we just talked about it, but I'm just kind of curious, and you're the person to ask. Compared to like the ISS orbit, which is really not that far, how far are the Hubble and James Webb, I guess, going to be from?
Okay.
How far out are they?
Yeah, the Hubble is only a little bit further up. So the International Space Station is like 150 miles up. Okay, low Earth orbit, or what they call LEO, low Earth orbit. Hubble is only like 200 miles up, so it's only a little bit further up. But when you launched the space shuttle, back when we had the space shuttle, you couldn't go to the space station and to that. There were different orbits. That's why once they had problems with it, the astronauts were like, "Oh, let's go to the Hubble," and they said, "No, we won't do that anymore," because now they always want to, no matter what, be able to go to the space station as kind of a safety thing. So if something goes wrong, you can always get to the space station. And if you went to the Hubble, you couldn't do that. So they said no, even though a bunch of astronauts actually signed the thing and said, "Oh, we'll go to it anyway," but they never did. And they've kept it running. I mean, we haven't had to fix it since then. So, but the James Webb Telescope is going to the L2 position. This doesn't have anything to do with overtime, but I'm going to explain this because it's kind of cool. Here's the sun, here's the Earth. There's 5 what they call Lagrange. I think this is the Frenchman. 5 positions in a 3-body system. Meaning you got the Earth, the sun, and then the other object. There are 5 what they call stable positions. Those are Lagrange points. The most famous one is between the 2. And it's called an L1 point. If you were at that point in space, hanging out, you would be balanced between the Earth and sun, you would just stay there. And that's kind of an unstable point, meaning that if you fell away from that point, you would just keep falling away. It's kind of like being on top of a mountain. As long as you stay on top of the mountain, you're fine. But if you fall one side or the other, you're not getting back up. There's also the L2 point, which is on the opposite side of the Earth. There's an L3 over here, And then in the Earth's orbit, 60 degrees ahead and behind, there's L4 and L5. James Webb is going to be an L2. Why? Because it's an infrared telescope. So it's, instead of being focused on the optical like Hubble is, it's going to be focused more on the infrared. Okay, you can see close to optical, kind of the infrared from low up, from the very, very red that we can see all the way into the very infrared. They got to put it there because the sun puts out gobs of infrared. So you remember, infrared is heat. So what do? You put it here, then it's blocked by the Earth. Essentially, the Earth is the giant shadow for the space telescope. You put it at this position and it'll always stay in the Earth's shadow. As it goes around the sun, the telescope just hangs out there. Now the problem, this is way, way up here. Meaning, if they screw it up, there's no going to fix it. Where they screwed up the Hubble, but the good thing is 3 years later, they went up and they fixed it. You can't do that with James Webb. You better not mess it up. $500 billion. You don't want to mess it up.
Is it farther than the moon?
What's it?
Farther than the moon?
No.
But far enough.
Yeah, I'm thinking, I don't know. I better not say because I don't remember the exact, but it's way too far to go to. Yeah. Now the moon is 250,000. The moon, I'm getting way off track today, but the moon and the Earth have their own points. One of the suggestions was, well, hey, you could put one at the L4 point of the moon Earth system. You put a space station. Perfect for flying off to like Mars. Because you fly up to this stable point, the space station at that point will always stay there. It's a very stable point, and then you don't have to get off of the gravity by like flying the moon and then trying to go to Mars. Well, you have to get off the moon, and so it takes a bigger rocket. But when you're in space, it takes almost nothing to get moving again. So that's a possibility as essentially a rendezvous point in the Earth-Moon system. They've used the L1 point numerous times. They've put satellites out here and collected like solar wind particles, because it just sits there and then it collects all these particles, and then they brought it back to the Earth. And it was stable there for months. All right, sorry, off track. Let's get back to telescopes. All right, so angular resolution. We can work this backwards too. What if I told you, I want to know what diameter of a telescope will let me see 1 arcsecond resolution? How would I work that? Yeah, so I can't put in sine of something in arcseconds, right? It has to be in degrees. So I have to convert 1 arcsecond to degrees. So what do I do to that? Well, I have to divide it by 3,600. Right? So if I do that, I do this calculator. Yeah, I got 2.77 8 times 10 negative 4. Is that what you get? Okay. So this is the angle in in degrees. Then what do? We rearrange this equation, right? And you're going to solve it for d. So we just rearrange that. We multiply both sides by d, and we get d is equal to 1.22 lambda over the sine of theta. Or we get d is equal to 1.22 times 5 times 10 to the minus 7th over the sine of 2.778 times 10 to the minus 4th. How do I know this is in meters?
Because you use
Because I put that in meters, right? And those are always going to be the same.
Is that 0.125?
Yes.
Okay. I just,
Or if you prefer, 12.5 centimeters.
okay. I just couldn't really see the decimal, so.
How big is 12.5 centimeters?
About 5.
Yeah, about 5 or 6 inches. Any telescope bigger than that doesn't increase your resolution on the Earth because of our atmosphere. So, atmospheres suck, don't they? But if we didn't have one, we'd all be dead. So, I guess they're necessary. You got a question?
We have a question about that 2 stars with 5 degree separation, right? So,
This part?
yeah, that part.
Yeah,
We
so
have a plus and we have the, right?
in theory, right? If you have a bigger telescope, you should be able to separate them.
No, I think you asked the question like how big your telescope should be to like see those 2 stars like separate.
Yeah.
So we haven't done that.
Yeah, well, there isn't really one because what I was trying to prove to you
Oh, okay.
is that you get a bigger telescope, it doesn't really matter. Okay, meaning the 10-inch, we should be able to see things to a half an arc second across. So we could easily see things that are 5 arc second across. Okay, but the problem is if the atmosphere is really disturbed and changed, it won't matter what size telescope you got. So the atmosphere makes a huge difference. And remember, you only need one this big to see 1 arc second. And that's not a very big telescope. So we're going to test that, not this week, but that's our goal next week. Because I'm going to give you a bunch of double stars that are really close together, some far, some wide, and see some far, some wide, that's the same. Some wide and some really close, and you'll see which ones you can see. And we'll see how good a night it is too. It also depends a lot on the night. A good night, you can find ones that you can't normally see. It also depends on how good your vision is. Some people have better vision than others. If you can't focus things really precisely, you still can't see them either. It just kind of blurs everything out. That's how I always tell when my vision's not doing well is when I go outside, the stars don't look like pinpoints. When they start to look a little like flops, you need to go to your eye doctor and get your vision checked. Your prescription is off. I wear contacts, and so the first thing I notice is like, oh, the stars are a little big. My eyes have changed, and contacts need to be changed. All right. So far, so good. How does the telescope work? You have originally, who invented the telescope? Guy named Hans Lippershey. I used to pronounce it Lippershey, but then somebody told me that's wrong. The S actually goes away. It's the Lippershey. I don't know. He was Dutch. If you're in the Netherlands, that's the way you pronounce it. He created what we call, or what he called a spyglass. It was a way to see things close up, right? And then 1 year later, Galileo had heard about this and invented his own without ever seeing one. He just heard somebody did it and then he went and did it himself. So lots of people give Galileo credit just because they know his name, but he really technically wasn't the one. But he never saw it. He just heard that this thing was created, so he made his own. In fact, this is a replica of Galileo's telescope. 2010 was the 400th anniversary of Galileo making a telescope. So they sold these replica kits as a way to get people like me to waste money on it. But it says right on here, replica Galileo's telescope. This is about how big it is. This is the right same size and everything. He had a lens back here and a lens back here. And that's all he needed to make a telescope. So what happens is the one closest to the front we call the objective lens because it's closest to the object you're looking at. For astronomy things, all light comes in parallel because they're so far away. There's no divergence by this point. the light then gets focused to a point. This point's called the focal point. And the most important thing for any lens is the distance between the center of the lens and the focal point is the focal length. Okay. So what that means is all light, stars, planets, whatever you're looking for, all that light gets focused to a focal point right here, to a point right close to that. Creates the image at this point. Slightly in front, slightly behind, but close to that because everything's at infinite distance. Then to make a telescope, you just put another lens here, what we call the eyepiece. And you magnify the image created from this one. So this one creates an image, then you magnify the image with the eyepiece. So that's all it takes for the simple telescopes is 2 lenses. Nowadays, our telescopes and eyepieces have gobs of lenses. You see this one here. These are like the lenses, this is the new lens, just like the ones you use at a telescope. I'm just going to show it to you in daylight. I don't know if you saw them. Last time you used them. Does it look familiar? This is a 20, no, this is a 35 millimeter. What does that mean? Not wide, we don't care about width. No. Focal length. Focal length is everything, right? But you're like, wow, $600 for a lens? Well, inside there's actually 7 different pieces of glass. Well, this is a Panasonic, yeah, probably 7. Some of them have 5 or whatever. Like, why would he have so many? Well, that's how we get nice, beautiful images. Galileo, when he looked through his, yeah, even at the best of times, it was fuzzy. He really couldn't tell Saturn had rings. He called it the ear planet. Because he said there's something weird there, and then the ears disappeared. What happened is the rings actually turned the edge on a few years later, and they went away. But he couldn't really tell that they were rings. It only takes a 30-power telescope to do that. But his telescope, you know, the optics and stuff weren't anywhere close to what we are now. But that's why this costs like $600. Because it's all, and all of it has to be optically corrected and coded and all kinds of cool things. Makes it really nice, but it's very expensive. That's why it's nice. People ask me, you're an astronomer, do you have a really big telescope? It's like, no. Because everywhere I work, I have access to way better telescopes than I could afford on my own. So why use why buy something for myself when I can just use better equipment?
Right.
Especially when I'm the one that runs it, I can use it whenever I want.
Yeah, unless you can use it as a recreational, I guess.
Oh, I do, yeah. Sometimes in the summer, I can just go out and use them whenever I want. Helps to be the observatory director, right?
Yeah.
All right, so that's the eyepiece. We can switch out the eyepiece depending on what we want to do. So in a telescope, you can change that. And Galileo had that too. He had 2 different eyepieces. You can take out the eyepiece and put a different one in. And he realized when he did that, it changed the magnification. What's magnification? What's that?
How big you make what you're looking at?
Big compared to what?
What you originally saw.
Yeah, what you would see without any magnification, right? So comparing how big in arc seconds or arc minutes it is compared to what you'd see with your naked eye, right? Well, it's an easy calculation because both of these lenses, right, have their own focal length. This is the focal length of the eyepiece. This is the focal length of the objective. The magnification, M, is just the focal length of the objective divided by the focal length of the eyepiece. Just a couple examples. Our 10-inch telescopes, the ones that you use, well, they might have changed. We'll have to look at the telescopes because we use different ones now than we used to. But the ones we used to use have an objective focal length of 2,500 millimeters. They're usually given in millimeters. Okay. And what eyepiece do you usually use? What did I tell you to get? It's like a 26, right? Let's make it a 25.
That's pretty close.
Close enough, right? And it makes the map a whole lot easier, doesn't it? So the magnification is just going to be 2,500 divided by 25. And you just do the magic 25 crossing property. What they call it, math class, right? And you actually get what? It becomes 100 power. So typically, we're running the telescopes at 100 power, give or take, 80 to 100. What if I put the 35 millimeter on there? Would it get more magnification or less? Less, right? So the bigger the eyepiece, the smaller the or less magnification. Oh, what's that?
Because the bigger denominator makes the number smaller.
Exactly. So if I wanted to zoom in, more magnification, I would use a smaller focal length on the eyepiece, about a 17 or so, give or take. We actually have down to like 13s, but there's limits on that. What you find is you get above about 140 power or so, you gain nothing. You're like, oh, so you see Saturn, and you're like, oh, I can make it twice as big. Yeah, but it's twice as big and just twice as fuzzy. You didn't gain anything, you just made a bigger fuzzy patch. In fact, some things actually look better smaller. If you're looking at faint objects, it's better to leave them small and have because all the light's coming from one spot instead of spreading out the light, and then your eyes have a harder time seeing it. So if you're looking at faint galaxies or nebulae, you want to actually have the lowest magnification you can get away with. If you're looking at things like planets, then you try to get away with as much magnification as you can because there's so much light and there's detail. You try to do as good as you can, or if you're looking for binary stars, zoom in on the thing. Okay, let's talk about field of view. Field of view. So when you look through the telescope, you see part of the sky, right? That's the field of view. It's usually done as FOV, field of view. What we're really saying is we want to know how far across on the celestial sphere that is, usually in arc minutes. So why did I put the slashes? Let me write it out in arc minutes. Okay. Now that changes with every single eyepiece, because if you have more magnification, what happens to your field of view? It gets smaller, right? Because if you had something that was really tiny and you zoom in on it, it gets bigger. Well, what you're just seeing is less around the outside, so your field of view gets smaller. So the field of view is a function of your magnification. The lower magnification, the more you see. Higher magnification, the less you see. Okay? Now, the field of view, you can actually calculate it, but it's kind of complicated for telescopes, especially for modern telescopes. Because like our telescope here, this is an 8-inch, but it's just like the 10 inches that you use. Identical, it's just a little smaller in size. But remember, the light comes in and bounces around in here. And then it goes here and bounces off the back, comes up here, and then you have your eyepiece. And you got to get all that calculations and everything in there, and it's kind of complicated. It's easier to just measure it. How do you measure that? Well, we're not going to do this tonight, but you're going to write this down because this is what we're going to do next week. Next week, I want you to measure the field of view using 3 different eyepieces. A small one like a 17, 13, 26, and like a 35 or a 40. We have a 40 something out there too. What you do is you look near the celestial equator. You find a star near the celestial equator. How high is the celestial equator from Commerce? No, try again. 57, right? 33 is the north celestial pole. The celestial equator is 57. So you're just going to point your scope up at 57 degrees, or on the side of it, you just put it at a declination of 0, right? That's right on the celestial equator, right near the meridian, because that's when the stars are moving across and they're making the biggest arc. Okay, you don't want to look up near the north celestial pole or real down low, because those stars are making smaller circles than normal, right? Then we're just going to turn off the drive, meaning normally these follow the stars. But if we turn it off, we can use the rotation of the Earth to figure out how big it is. So what you're going to do is you're going to be watching, and a star will either start on this side or this side. You're like, why wouldn't I know? Well, it depends on which way you have the eyepiece flipped and the extra thing. Because every time you use a mirror, you flip the image. It's like when you look at yourself in your mirror, your right and your left are flipped. But if you put another mirror, you're going to flip it again. You put another mirror, and we have 3 mirrors in there. So it's complicated. Okay. But what's going to happen is you're just going to time it and see how long it takes that star to go all the way across the center. How does that tell us the field of view? How fast is the Earth rotating?
15 degrees an hour.
Okay, yeah, we started out 360 degrees in 24 hours, right? Which is how we got 15 degrees an hour. Okay, how many degrees a minute?
That times 60.
No, that divided by 60, right? It's a fourth, yeah, 1/4 of a degree per minute. Right? How many arc seconds per minute? We got 1 degree. No, we multiply by 60. Right? Because 60 arc minutes over 1 degree, the degrees cancel. And we get 60 over 4, which is 15 arc minutes per minute. Right? How many arc seconds? Yeah. Or let's do this. How many arc minutes per second? Divide by 60, and what do you get? You get a quarter. Are you with me? Notice how it alternates? 50 a quarter, 15 a quarter. Because you're always doing the same 60, right? Okay, so what I really want you to know, and just write down this, is you're just going to time how long it takes to go across. If it takes 60 seconds to go across, what's the field of view? No, 60 divided by 4, right? 15. Essentially, you're dividing everything by 4. If you do it in seconds, you divide it by 4. Tells you how big the field of view is in arc minutes. Now remember, this only works if you're looking near the celestial equator. And you want to make sure the star goes across the center. Don't have the star go across up here. That won't work. And do this for 3 eyepieces. 3 different eyepieces. Can't use the same one 3 times. Next week, write this down. Because next week we're just going to review in here, and then we'll go out to the observatory, and you can do that. Tonight you're going to do what we were supposed to do last week. We did that too. Yes, the colored stars is what you're going to look at tonight.
What's going to change the IP?
Sorry, sir?
No, what's going to change if we change IP?
The field of view will change. So it'll take a different amount of time for a star to go across. Because the more magnification, which means the smaller the focal length of the eyepiece, the less of the sky you see. So the star will go across it in a shorter distance. Because the star is going to be moving at the same rate. It's just a question of how much of the sky you're seeing.
I was thinking about short period, so that doesn't matter, right?
It doesn't matter now. Yeah. All right. So good? All right. Let's talk about limiting magnitude. limiting magnitude is another equation for you. It's 2.7 plus 5 log D. Where this is the diameter, I believe in millimeters. Yes, in millimeters. Yeah. So if there's a calculator, do logarithm, make sure you do log base 10. Don't do LN, that's natural log, don't do that. Do log, just LOG, and it's on your calculator, it'll be log base 10. If you get really fancy calculator, you can do log base anything like it, Spire or something, but don't do that. Just do log base 10, right? So let's put in our biggest telescope, our 27 inches, 700 millimeters. What this is saying well, if you put an eyepiece on it, how faint of star, or what magnitude can you see with just your eye? So if you do the calculation on that, you just put in 700. Yeah, you got 16.9. So the magnitude of the faintest object you can see with your eye is 16.9. Now, if you take a picture, we can see way fainter than that because your eye problem is that it can't calculate, add up light. Your eye has a shutter speed, about 1/30th of a second. You can't change that unless you're a cyborg or something. Okay. What if we did a smaller telescope? Like let's do an 8-inch telescope. Or actually, let's do our 10-inch because it makes the math easy. This is about 250 then, right? 254 or so.
14.6.
Yeah. You get around 14.6. So the faintest stars you can see about 14th magnitude. This is 16th magnitude. If you get down to smaller and smaller telescopes, it's less and less. So the bigger the telescope, the fainter you can see, which makes sense because you get more light. And that's just with your eye, right? It doesn't have anything to do with taking pictures. Taking pictures, you can take a long exposure and get way fainter than that. We can easily, in our 700 or 27-inch, we can easily get down to 22nd magnitude if you take a long exposure. And I'm telling you, the Hubble Space Telescope can get all the way to 30. All right, couple more things. Back to here. Focal ratio. Usually written as like this, f/8 or f/10 or f/6. That's the ratio of the focal length to the diameter. So for example, our 27-inch telescope has a focal length of 4,540 millimeters. What's its focal ratio? Divided by 700. This is the diameter, right? And so we just take the focal length divided by the diameter. So you would just take 4540 divided by 700 is the focal ratio. In this case, focal ratio. You get the focal ratio is about 6 point something. 6.5. The shorter the focal ratio, the smaller that number, the brighter the stars appear. But there's other problems with it because you have to have a faster curve and it change other things too. But also, the smaller that number, the smaller your telescope. Right, if you have an f10 and it's 10 times the size, the focal length is way out here, you have to have a lot bigger telescope. The smaller the number, the shorter your telescope. So that's why these get away with being very short. Two things, you bounce the light back and forth, but also there's a lot of curve there compared to some telescopes. All right, questions about focal ratio? Yeah, I guarantee you, it's be on the next one.
So when you wrote F over, was that supposed to be R or was that? F?
Yeah, sorry.
Okay.
This is the focal ratio. This is usually a number.
Uh-huh.
It's typically F8. That's why I wrote down an 8. But focal ratio is anywhere usually from 10 to like 6 are typical. But it can be anything like that. Now, I talked about this being a lens, but we don't use lenses. What do we use? Mirrors, right? So the mirrors have focal length. What's the difference?
Only weird shaped mirrors that focal
Only weird shaped mirrors. Yeah. It's definitely not a. This is an actual astronomical one. It's been ground to better than wavelength, a quarter of a wavelength of green light, essentially. So there's no bump on there bigger than 1/4 of the wavelength of a green wave, which is like 1/1000th of a millimeter. So it's super smooth. That's what you do. And then you silver it, or sometimes illuminize it. It doesn't really matter. They're both very shiny, right? And with telescopes, big telescopes, every year or so, they actually re-illuminize it. They take the whole mirror out, they clean it off, and then they put it in this big machine that uses electrolysis. Essentially, they charge this, and all the atoms from the aluminum and stuff coats the surface into a perfect smooth surface. Okay, for amateur ones, we usually don't do this unless it's like 20 years old or something. You might do it, but just because it costs a lot of money and it's a pain to do, and a lot of telescopes that are built that way. This was, we did a whole workshop where people built their own telescopes, and we had some leftover one. That's why I have a leftover astronomy mirror. This one has this is a 6-inch. So that's the diameter of it here. And it's an F8, I believe. So where's the focal point? Yeah, how much? If it's 6 inches and it's an F8, it's
8 inches.
oh, 8 times 6. 48, right? Because 48 divided by 6 gives us a focal ratio, right?
Here's the
8 times 6 is 48. So if you're going to focus it, it's going to be 48 inches away when you focus it. Okay. And when you build your own telescope, which I built my own telescope when I was 14, I had to calculate all those things. I determined the focal length of the mirror. Then I had to figure out where to put the secondary mirror to bounce it out the side, and where to put the eyepiece so that all of that would calculate to the right position. When you focus a telescope, all you're doing is moving the eyepiece in and out. Because as it changes the temperature, mostly it changes the temperature, the telescope and the air will change, and you got to focus it in or out as the temperature changes. Which is why you have to do that. All right, so that is a astronomical mirror. These have astronomical mirrors too, right? Which you probably should have. Did you look? Did I show it to you? I probably showed it to you with the 10, right? When you get down there, if you didn't look at it before, look inside your telescope. Just don't touch the front.
Yeah, I think you did show us.
I did show you. Yeah, you see the mirror at the back.
I think I remember you pointing into it while you were doing this stuff.
All right, let's talk about telescope designs. Oh man, I'm running long today. It's because you guys made me talk about Lagrange points. Let me hold on. Send the text to Dr. Davis because I think she does need observatory wondering why we're up here. So I told her 7 o'clock. It's like we're not even at 7. All right, so telescopes like this that Galileo made using lens have problems because of lenses. One of the problems with lenses is as light goes through of different wavelengths, the focal point is different for different wavelengths. So blue gets focused in a different place than red and focused in green. There's no way to fix that easily, especially back then in the 1600s. We called that chromatic aberration. Remember, aberration is just a flaw. Chromatic means color, so it's a color flaw. And that light gets focused at different points. Because the nature of light as it passes through glass, the different ways get focused at different points. That's why we can use a prism to create cool colors, right? Now you can't get around that nowadays using what they call achromatic lenses. You put one lens of one kind of glass that makes the light split one way. You put a different kind of glass that makes the light split the other way. And they counter each other out and you bring it back together again. Very expensive, but you can do that. They're called apochromatic lenses. We have a couple of refractors that are piggybacked on our 16 and our 700. They're about 5 inches across. Those telescopes themselves are about $7,000. So for a refractor, you're paying a lot more for a 5-inch refractor than you are for a telescope that you can get a 10-inch telescope for. Mirrors are cheaper, easier to make. The other thing about lenses is the lenses have to be perfect. Meaning all the way through, if there's something inside the glass, it'll mess up your light. Where a mirror, only the one surface has to be perfect. If there's bubbles or something in the glass, who cares? You just have to make the surface perfect, right? All right, so that's one of the flaws with that. There's other flaws called spherical aberration. If you make a spherical surface, the light doesn't actually focus to a point. It's a spherical problem. What you really need to do, you use a mirror, and you actually make this shape a parabola. And then you can focus it exactly to a point. If you remember the definition of a parabola, so remember how you define a parabola.
X squared.
Yeah, but what is it geometrically? Every point on the parabola, it's the difference between the distance from a point on from a line to a point. So no matter where you pick on that parabola, you subtract those distances, it's always the same. You remember any of that? In ellipses, the sum of the distances to the two foci is always equal. What are they teaching in these math classes?
We don't have a general.
All right, well, the light from a mirror focuses to a point right here. So the stars over there, light's coming in, but if you put your head in here, you couldn't see anything because you blocked the light. So Isaac Newton realized that, hey, to get rid of this problem, we got to quit using lenses, let's use mirrors. And he designed the first refracting telescope. He put a secondary mirror in here, bounced the light out to the side, then put the eyepiece out on the side. This is what's called a Newtonian telescope, named after Newton. And yes, this has to be parabolic if you want it to be perfect, which is tough because machines don't make parabolas perfect. They're hard to do. You can make spherical perfect, but making parabolas is not so easy.
It says there's a mirror to an eyepiece down below.
Yeah, so this is what we call the secondary mirror. This is the primary mirror, or sometimes called the objective mirror, because that's the one that's the big one that matters. Right? Well, that's not the only way you can design it. We can also design what we call a Cassegrain, named after the guy that designed it. He said, well, let's just have our mirror here, but instead of bouncing light out to the side, we're going to put a mirror that bounces the light through the back. And you drill a hole in the back of the mirror and let the light through. And then you put your eyepiece back here. That's the Cassegrain design. Clever design because it actually works better than this. This problem with this works fine in a lot of amateur telescopes are Newtonians. Because you can make them cheap, and all your money goes into making your mirror as big as you want because that's what really matters. But if you're trying to hang like instruments on it, you don't want to hang them off the side. It unbalances it and doesn't work very well. So big telescopes all use Cassegrain. You say, well, you drill a hole, you lose light. Well, it doesn't matter because you already had a secondary mirror, which is blocking the light right in the center anyway. So whether there's a hole there or not, doesn't really matter. It didn't really hurt anything. All right, so
How come that doesn't show up in like?
It
I
does.
have a spotting scope that's Cassegrain. I can't, I don't feel like a hole.
you would if you're way out of focus. I don't know, some of you the other night were way out of focus and your stars look like what? They look like donuts. You know what you're actually doing is you're seeing this eyepiece or this mirror up in front of you here. So instead of a star being a nice circle, your star looks like a donut. What you're really seeing is this thing out here. But if you focus it, then all that light goes to that point. Yeah, you don't even see it at all. And it works for camera lenses, spotting scopes, whatever, right? All right, then companies like Meade and Celestron, many, many years ago, like 30 or 40 years ago, realized we want to mass produce these. And mass producing, like I said, it's hard to do parabolas. Pretty much that has to be drawn by hand. But I can make a machine that makes a perfect sphere. So what if I make it spherical, but then out here, I put a corrector plate so that when the light comes in, instead of coming in straight, it actually bends it slightly outward so that when it focuses it here, even though it's a spherical curve, which would normally be a problem, it still makes a perfect focus because you put a corrector plate out front. And this corrector plate is made of glass and you can just pour that, that's easy to make. And then you get machines that make a whole bunch of mirrors and you can produce a whole lot of them, you can produce it cheap. And because the light is bouncing back and forth, you can make them short. These are called a Schmidt-Cassegrain. Or lots of times they shorten this to SCT or Schmidt-Cassegrain telescope. That is exactly what that design is. It's the ones you use. That's why there's a piece of glass up here. That glass is actually affecting the light, but it's affecting the light to make it so this spherical mirror back here bounces, and then there's a mirror behind this black thing here. Light bounces back to the back, comes through, hits another mirror, which bounces out the side because it's easier to see. If you didn't have this here, it still worked, but then you're down here trying to look like this and your neck gets really sore. So this makes it easier, and I showed people that when you turn, you loosen these up, right? You can rotate this to make it more comfortable to view because it doesn't really matter which direction it is. Okay. So the telescopes we use are Schmidt-Cassegrains. Now our 27-inch is actually called the Naismith. Which is another design. In the Naismith design, it's like a Cassegrain. You have a mirror back here. Light comes in. It hits a secondary mirror up here. But instead of like doing a hole through the back of your telescope, you actually put a third mirror in here or a tertiary mirror, and you bounce the light out the side. And it goes right through the middle of your mount. Because you have these two forks here. So what it does is instead of the light coming all the way back here, there's another mirror in here. It bounces it straight out the side through a hole in the side. The cool thing about that is that when you strap your camera on there, the camera doesn't go up and down and get out of balance. It always, only thing it does is rotates around. And you can have one side with a camera, and then you can flip this mirror. We have a button and we just hit it and it flips around. You shoot out the other side and there's an eyepiece. So you hit it one way and you can look through the telescope. You hit the other way and take pictures. It's called a Naismith. You can also bounce it down through the mount so it comes out the polar axis, so then it would never move. That's called a coude focus. So there's all kinds of cool things you can do with those things. They use that for very elaborate spectrographs. There's some spectrographs that are so fine and so delicate that you can't move them around and the temperature has to be perfect. So they actually take the telescope light and bounce it all the way down to like a room under the telescope where this giant instrument is. And it's perfectly in a nice environment where the temperature is perfect and it's completely dark and everything. So You don't have to worry about the instrument being on the telescope, you just bounce the light to it. You don't see that much nowadays. In fact, most telescopes nowadays are either a straight Cassegrain or the Hubble-Everly telescope. They just put the instrument up here, and you just focus it to that point. You don't have to have a secondary one at all. You just focus all the light to this detector, which is hanging out over the telescope. Works good too. All right, which telescope is better for what? Well, it's not really good, better, or worse. It just depends kind of what you're looking at. If you want to look at something that's very big in the sky, like you're trying to look at the Pleiades, right? They're like close to a degree across. If it's something a degree across, if you have a telescope that's got a very long focal length with a lot of magnification, you're never going to see the whole thing. You look at it, you'll see 1 or 2 stars, and you're like, looks terrible. So what you want is really low power. So you use a really small telescope. So some things look bigger in small telescopes or even binoculars. The Pleiades look better in our binoculars than they do through any of the telescopes. The Andromeda Galaxy actually looks better too. When you put a telescope on there, all you see is the center, and you see this fuzzy patch. You're actually not seeing the whole thing. So things that with a large angular size are better in smaller telescopes. Things that are very bright, tiny details like planets, then you want a really big telescope that you can zoom up the magnification as high as you can. As good as the night will let you go. Or if you're trying to look for binaries that are really close together, use the biggest telescope you get. The other thing is you're looking at something very, very faint, like a galaxy. Galaxies are very faint. Then you want actually the biggest telescope you can, because you want to get as much light as you can get. Biggest telescope you can at the lowest power you can run it at. So it depends on what you're looking at, what's best. Yeah. Questions about any of that? Got one more thing for you. So write all this down. These are for next week. These are the stars I want you to look at, the binary stars I want you to look at. All right, Almach, which is Gamma Andromedas, by the way, if you're curious. It has a separation of 10 arc seconds, the 2 stars. Epsilon Lyra, which is interesting because it's a double-double. Meaning at low power, like through the finder scope, you see it as 2 stars. But at high power, each of those 2 stars becomes 2 more stars. So it has separations of 208 arc seconds, which is for the big one. And then once you get those, each of those is 2.3 arc seconds by 2.3. Very tiny. Beta Scorpio, which is very bright, second brightest star in Scorpio, so it's a very bright star. 14 arc seconds. Gamma Delphinus, 10 arc seconds. Rho Hercules, 4.1 arc seconds. Sigma Chi, Cassiopeia, 3.2 arc seconds. And then Struve, 3053, which is 15 arc seconds, but it's cool because it has different colors. I'm going to make this easier for you, so write these down too. When you put them in the telescope, it's easier to put in the SAO number than to search for their names. So these are the ones with the SAO numbers. Oh, I messed up. Sorry, hold on. Don't write anything down yet. Oh, the left one out. Okay. And Alpha Hercules, which is the brightest star on Earth, Hercules, which is 4 arc seconds. And the name of the star is Rosaligetti. The cool thing is it's right across from the brightest star in Ophiuchus, which is Rosaligetti. It's cool because they're just fun to say. Rosaligetti and Rosaligetti. What's even cooler are the stars in Lyra, which is Zuba el-Jubi and Zuba el-Janat. All right, these two don't have SAO numbers because you just look up the name. These don't have names in it, so it's easier to look up the SAO number. We're gonna do that next week, but just have that all for yourself next week. All right, let's head out to the observatory. Hold it. I forgot. Yes. It's a really great day. I thought you would think it was astronomical.
That's the first thing I thought.
No, when somebody, we're going back to the last one,
See you out there.
so when somebody brings up a date, it's either an anniversary or a birthday.
And as soon as your whole group gets out there, you can start setting up and half away from me. I might be a little bit late, so I gotta take this up.
I'm going to the lounge.
Well, I'm gonna take my.
You want me to keep-
Whoa.
It's not a big-
It's out, as well.
By the way, do you go have these?
I have 2. I think that's enough for today. I might get some next.
Yeah, next week we're probably gonna need some more,
Okay, we'll get through tonight.
yeah.
You might need 2 for tonight, but 2 should make it.
Yeah, then next week we'll definitely need more, I think we all have like 2 each left.
Okay. Oh. Recording.